Right. Let's say the electronegativity. What is electronegativity? Tendency to attract that electrons towards itself. For example, here we will see these are the seven group elements here. Negative elements. Fluorine, bromine, nitrogen. Right. So tell me which is more electronegative among these? Fluorine, bromine. Right. Right. So here fluorine, bromine, right? Fluorine is a more electronegative. Then chlorine, then bromine, then iodine. Right. So these are the electronegative atoms. And when these particular electronegative atoms are attached with the protons, when these electronegative atoms are present adjacent to that proton, okay, then it will be influence the chemical values. Right? And generally, the electronegativity increases the delta values. Okay. So presence of electronegative groups increases the delta values. Okay. So for example, here this one CSC chlorine. Okay. CSC, F, CSC, Cl, CSC, Br, CSC, iodine. Right. So then, now you can see here the CSC, F, right? CSC, Cl, CSC, Br, CSC, iodine. So from top to bottom, the electronegativity increases or decreases? Decreases. So delta values, right? Delta values of these protons, right? That means CSP, more means having the higher delta values, CSP, yeah, sorry, chlorine, yeah, right? We can have it approximately 4.685, 4.76 delta something. It is if I take around that, and then it is 2.6 something, 2.3 around that. So you see, all are having the same groups. Here you can see the CSC, here you can see the CSC, here you can see the CSC, the CSC. All are same methyl groups only. Same number of protons are there, right? But this CSC is attached with chlorine. This CSC is attached with chlorine. This CSC is attached with bromine. This CSC is attached with the iodine, right? So due to the difference in the electronegativity, the delta values are changing. Means changing. Like this is actually right? So this is the electronegativity. Yeah. That means presence of electronegative atom increasing the temperature. Okay. And with increase of number of electronegative atom, the delta values will be. For example, here. Yes. Okay. And CS2. Okay. Here we have something, right? Then it is CL, right? CH2, then we have some 11, right? ఇక్కడ టూ chlorines are there. So, but ఇక్కడ ఒకటే ఉంది కాబట్టి increase of the number of electronegative atoms, also reasoning for the higher delta values. Okay, అక్కడ ఒకటే electronegative atom ఉంది, ఇక్కడ రెండు electronegative atoms. You can observe the higher delta values. That means the signal appears in the downfield, appears in the left side in the graph or downfield or deseated region, deseated. Okay, downfield or deseated region. And the second factor is the anisotropic effect. Anisotropic effect. So what is anisotropic effect? Anisotropic effect. So here, when a molecule or the compound is exposed to the external magnetic field, then the produced field, the effect, okay, the produced effect will be distributed equally on each and every atom of the molecule. Okay, if it distributes equally to the all the atoms present in the molecule, then it is called the isotropic. If it is distributed unequally, then it is called anisotropic. Clear? So, for example, here in molecule, now we say here, right? And we are applied the magnetic field. This is the external magnetic field. Here, the external magnetic field. Right? So we are applying this external magnetic field to this particular methane molecule. We have the molecule, right? So the effect produced, right? The effect produced due to exposing of this molecule, it will be distributed equally to all the atoms in the molecule. Right? This is your the effect whatever comes. Right? Ring current, you say it is the ring current. So it is distributed equally to each and every atom in this methane molecule. Right? If it is distributed equally to each and every atom, then this effect is called the isotropic. Right? It's called the isotropic. In case if it is not distributed equally, every atom, if it is distributed unequally, partially, then it is called the anisotropic. Okay? So the anisotropic effect also one of the major factor which is influencing the delta values. Okay? So if you see the delta values, temperature values in that particular table, which is given here. So if you observe that values, for example, here alkanes. How much it is? 0.5 to 0.9. Alkenes. 12.6 or 5.7. Alkynes. 1.5 to 1.5. So the first factor is the electronegativity. Okay, electronegativity. So what is the effect of electronegativity here? With the increase of the electronegativity, delta values will be increases. That is a directly proportional. Electronegativity directly proportional to the delta values. Right? So if it increases, it will be increases. Okay, that is directly proportional. So generally, for this single bond double bond, alkanes, the electronegativity order is triple bond is more hybridization. Okay, electronegativity of this sp, then sp2, then sp3. This is the electronegativity order. That means alkane, alkynes, alkenes, then alkanes. This is the electronegativity order of your various functional groups. Alkynes are, that is sp hybridized carbons are more electronegative in nature, then double bond, then single bond. Single bond is a more electronegative in nature. Okay, that means which is strong bond among this bond, double bond, triple bond. Which is strong bond? Triple bond. Single bond. Single bond. Strong bond. Single bond. Okay. So electronegativity is sp, sp2, sp3. Okay. So as per this, okay, as per this, like electronegativity factor, according to the electronegativity factor, with increase of the electronegativity, the delta values must be increases. Okay, that is a statement. As per that, alkene must be having the higher delta value. And then, this is more electronegativity. Alkenes to sp ratio. What happens to alkynes? Sp. Alkynes sp. This carbon is sp. sp2. sp3. Hybridization. Okay. So, right. So here the sp hybridization is more electronegative than this. Right. As per electronegativity factor, so the alkyne is supposed to have the higher delta value. But here you see the right 0.5. Okay. 0.5 you critically okay. So it is more than 4.5 not. Okay. As per that statement, as per the electronegativity factor, it must be 4.5 to something 6.2 whatever. Right? But ఇక్కడ deviation వచ్చింది. Your alkyne is deviating. Okay. It is deviating the order, electronegativity order. Right? So to explain this, the deviation in the electronegativity of this alkyne, we have taken the anisotropic effect. Okay. So this disorder of this electronegativity factor, right, is due to the presence of anisotropic effect. Okay. So anisotropic effect means generally this is depends on the orientation of the molecule in the packet. Okay. The anisotropic effect is observed. Okay, is observed based on the orientation of the molecule, location of the molecule in the external magnetic field. Okay. So if any molecule, okay, located perpendicular to that particular external magnetic field, it will have the higher delta values. Is parallel to the external magnetic field, then they will having the lower delta values. Okay. So I will explain. For example, you see alkyl. So there is no issue with the alkane. Okay, but previous name was only alkene and alkyl. We learned the difference. Okay, alkene కంటే ఎక్కువ ఆల్కైన్ ఉండాలి. డబుల్ బాండ్ కంటే ట్రిపుల్ బాండ్ వాల్యూ ఎక్కువ ఉండాలి. బట్ డబుల్ బాండ్ వాల్యూ ఎక్కువ ఉంది, ట్రిపుల్ బాండ్ వాల్యూ తక్కువ. కాబట్టి ఈ రెండింటిలో డిఫరెన్సెస్ అది ఎందుకనేది మనం చూద్దాం. ఫస్ట్ విల్ సీ ద alkene. The alkene protons, the protons here. So we place this alkene, the external magnetic field, the direction of the magnetic field. Okay. So then we produce the secondary magnetic field. The primary external magnetic field. Okay? Then it is right. So it is producing the secondary magnetic field. The direction of magnetic field. Okay. So this is secondary magnetic field. New effect. The new effect produced when we apply the external magnetic field. Okay. So this new effect is okay. So it is the new effect, and generally this region, right? Okay. So this region is called the paramagnetic region, and this region is a diamagnetic. Okay. So this region is a diamagnetic region, and this region is a paramagnetic region. That means this particular alkene, a polyphenol alkene, right? So it is oriented perpendicular to the external magnet. Right? So here the carbons are falls in the diamagnetic region and the protons are falls in the paramagnetic region. So if any atom falls, if it falls in the paramagnetic region, it will be decerial. Decerial. That means higher, and any atoms falls in the diamagnetic region, so it will be serial. Okay. Same thing we'll observe for this alkyne. So here the alkyne is located parallel to the external magnet. Okay. So we are applying the magnet in this direction. So the new effect is produced. The protons attached to the carbon here. The secondary magnetic field. Now we see this is the paramagnetic diamagnetic. Right? So now we see the orientation of the the orientation of the protons. Here you see the protons are oriented in the paramagnetic region. So they will experience more external magnetic field and they will be seated. Sorry, de-seated. So they will appear in the de-seated region and higher delta values. And here is the two protons, the acetylene and the alkyne. Okay. So the two acetylene protons are falls in the diamagnetic region, right? Diamagnetic region. So they are not experiencing the secondary magnetic field, right? So usually they are escaping from this secondary magnetic field. If they experience the, if they face the secondary magnetic field, so then they will have the more delta values. Okay, but the location of this one, the orientation of these protons are parallel to the magnetic, other external magnetic, right? So కాబట్టి మనకి ఇక్కడ the newly produced, right? Newly produced effect, that is a secondary magnetic field, right? Is not experienced by your protons, typically protons. That's why these protons are showing the less delta values, and the olefinic protons are falls in the paramagnetic region and they are experiencing the secondary magnetic field. So they shows the higher delta values. So this effect is called the anisotropic effect. That means this new effect is not distributed equally to all the atoms here. Okay. So ఇక్కడ ఇప్పుడున్న atoms మనకు ఈ secondary magnetic field ఇక్కడ experience అవ్వట్లేదు only these protons. Okay. So ఇక్కడ వచ్చేసి the orientation, how it is oriented. That's all. Molecule orientation is important. If it is oriented parallel to that external magnetic field, then they will experience less magnetic field. They will fall in the upfield, or they will show the lower delta values. If they oriented perpendicular, right, perpendicular, then the protons experience more external magnetic field. They will which shows the higher delta values. This is okay. And benzene also. If you take the benzene, which is the direction of applying of the magnetic field. And newly produced is produced gas. So you see all these protons, here three protons, here three protons. Benzene, the molecule formula is 666. So six protons are okay located in the paramagnetic region. The paramagnetic region. Right? So they are present in the paramagnetic region. So these protons experience the more delta values. Okay. And here also these three protons. Total six protons are falls in the paramagnetic region. So they will shows the higher dental value. So మన benzene వచ్చేసి aromatic ring కి okay aromatic protons right. So delta value equal to so H1 NMR spectra లో మనకి ఎక్కడ సరే ఇది signal multiplex is appears as a multiplex right మనకి 6 protons ఉన్నాయి కాబట్టి appears as a multiplex and that multiplex is always obtained in the region of right 6 to 8 you will get the multiplex in between 6 to 8 right so in the NMR spectra if you observe any multiplex in the range of in the region of 6 to 8 immediately you can suspect the multiplex 6 to 8 మధ్యలో multiplex signal కనిపించింది అనుకో so you can suspect the benzene so అక్కడ benzene ఉంది అనేది ఒక primary idea అంటే స్పెక్ట్రల్ అనాలిసిస్ చేసేటప్పుడు మనకు కొన్ని కీ పాయింట్స్ ఓకే సో కొన్ని మనం అట్లా కీ పాయింట్స్ పెట్టుకుంటే సో మనం నెక్స్ట్ స్పెక్ట్రల్ అనాలిసిస్ ఎట్లా వస్తుంది సో దిస్ ఇస్ anisotropic effect very important question start question లో 5 marks or 4 marks so 100% repeated every time so factors affecting the anisotropic effect start అవుతుంది సో మనకి ఖచ్చితంగా మనకి 10 మార్క్స్ ఈజీగా వచ్చేస్తుంది ఒకటి ఎలక్ట్రోనెగటివిటీ and anisotropic effect and the third factor is steric factor at the hydrogen bonding steric factor next effect is a steric factor so generally steric effect అనేది steric factor means bulkiness steric factor means the bulkiness okay bulkiness so here the steric factor also plays a very important role in the electricity generally if the proton is right, and actually here the steric factor where the it is increasing the delta values steric factors increasing the delta values factor increases delta values that is presence of bulkiness causing for higher delta values for example you see so here is a two next ones here it is right diethyl succinate. ATP trans. Trans diethyl succinate. Succinate acid. That's it. Bromide succinate. Bromide succinate. That's it. That's all. ATP. Folic acid. Folic acid. Folic acid. Succinate acid. Succinate అంటే మనం ఆమ్లసిక్ యాసిడ్ అంటే వేదిక యాసిడ్ ఒక్కొక్క సిఎస్ డిగ్రీస్ అవుతుంది. సక్సినిక్ లో రెండు సిఎస్ వస్తాయి. ఇక్కడ రెండు ట్రాన్స్ డైథైల్ సక్సినేట్ సిస్ డైథైల్ succinate. We have two isomers, trans and cis succinate here. Okay. Here both are carrying the protons, right? We have the protons here. It is symmetrical. So you can proton symmetrical కాబట్టి both are same. One non-equivalent. Yeah, only one non-equivalent. You get one signal, right? Signals. Signals. Right. This is transfer. So here is this proton. This is 6.9 delta value. It is substitute 6.2. Trans where the steric crowding is less. Steric crowding అంటే bulkiness rate తక్కువ ఉంది, repulsion rate తక్కువ ఉంది. So the transfer and opposite side also, right? Opposite side ఉన్నాయి కాబట్టి the proximity, right? Closeness is less. Both are very close. Okay, close ఉన్నప్పుడు repulsion ఎక్కువ. So ఇక్కడ మనకు ester groups, the two ester groups are in the opposite direction, so the repulsions are minimized. Yes, అదే ఇక్కడ మనకు both the ester groups are very close to each other. Two esters are close to each other. దగ్గర ఉన్నప్పుడు ఏమవుతుంది repulsion, right? So this repulsion దాన్ని మనం ఏమంటాం steric effect అంటాం, steric hindrance, called the steric hindrance. Steric hindrance or steric crowding. Steric hindrance or steric crowding. So steric crowding is more in the cis form, less in the trans form. So steric crowding results in the higher delta values. Presence of steric crowding, delta values will be increases. Okay. So మనకి ఇక్కడ steric crowding దీంట్లో తక్కువ ఉంది కాబట్టి తక్కువ సెట్ 6.3 డేటా. ఇక్కడ steric crowding ఎక్కువ ఉంది కాబట్టి 6.9 డేటా. Okay. Same both are isomers only. Two isomers, same molecular compound. So రెండింటిని మనం మిక్స్ చేసి మనం ఎటువంటి మనం రికార్డ్ చేసినప్పుడు రెండు సేమ్ కాంపౌండ్ ఒకే దగ్గర కలిగి ఇది వచ్చేసి పక్కనే పెట్టాము. So by this differences you can identify the isomers. మనకు IR స్పెక్ట్రాలో ఫింగర్ ప్రింట్ రీజియన్ ఉంది. ఫింగర్ ప్రింట్ రీజియన్ by using that finger print region, you can differentiate the isomers. So with help of H1NMR, so you can identify the isomers also. Right? Cis trans రెండు different data value. Both are appears with the different delta values. So steering factor, it is increasing the delta values. Okay. Next factor is the hydrogen bonding. Everything. Go ahead. Huh? Okay. Next, hydrogen bonding. Hydrogen bonding. So generally, hydrogen bonding also increases the delta value. Here the hydrogen bonding. Directly proportional to the. So for example, here alcohol. Right? So 50 so its value is around 3.2 delta. So you can see the difference of free OH. It's here, there is no hydrogen bonding. It's free OH, right? Without hydrogen bonding. It's not phosphating the hydrogen bonding. So this appears at 3.2 delta ppm. When this same proton is involves in the hydrogen bonding. So hydrogen. When this proton is involving in the hydrogen bond, intermolecular hydrogen bond, intermolecular hydrogen bonding. So when it leads to increase the delta value. When it is involving in the hydrogen bonding, where the delta values are going to increase, it becomes 4.6, right? So where the hydrogen bonding reasoning for the higher delta values, right? Because the hydrogen bonding it is transferring the electron cloud to the hydrogen. The reason for this having a higher delta values is the electron cloud. Okay, so this because the oxygen is a more electronegative, right? So this more electronegative atom. So it is transferring the electron towards this hydrogen, right? So electron density becomes more on this hydrogen. Okay, electron density becomes more on hydrogen. So electron density is going to be electronegative, attracting capacity. Okay, so electronegativity అనేది మనకి increase అవుతుంది. And మనం first factor electronegativity increasing the delta value. So same thing here. Due to increase in the electron density on the hydrogen, the delta value is going to increase. Right? So the free means the protons without hydrogen bonding having the lower delta values, and the protons when it is participating in the hydrogen bonding showing the higher delta values. So these are the factors which are affecting the temperature values. The electronegativity, anisotropic effect, the factor, and hydrogen. I'm stopping here, so we will see. So here, so when you see the NMR spectra of the uh, particular alcohol, so with this particular uh, two graphs are obtained. So generally the above one is where the impurity. When the alcohol is having the impurities, that particular the signals will get three signals for this one with different multiplicity. And when that particular alcohol is in the pure form, so we'll get the below below NMR spectra. Okay, so and if you see the difference of both the spectras, like in the above one, okay, so where the OH protons are appears as a singlet, uh, this is due to the proton exchange here. Okay, so due to presence of impurities, that proton will be exchanged with the impurities. So we'll get only singlet for this one. And in the pure form, so because there is no impurities present in that particular compound, so where the OH proton, it will be couples with the neighborhood proton. Okay, it couples with the neighborhood proton, that is CH2, and it appears as a triplet here. Okay, so CH2, where the two neighborhood protons are there. So total it is three, n plus one, according to n plus one rule. So it is there are three here. So it's split into triplet. Yes. So here the advantages of C13 spectra. So here the range of carbon chemical shifts are more here. Generally, if you see the H1 NMR spectra, the range is 0 to 20 ppm. But for C13, it is 0 to 240 ppm. So where the scale is very large. So it is easy to analyze the spectra, and where the appearance of signal, okay, the appearance of signal is very clear. And the chemical shift differences between the different types of carbons are more as compared to that proton NMR spectra, right? So where the chemical shift differences for this carbons are, it is high, right? So because the scale is very large, 0 to 240, yes. So yeah, the clear separation of these signals is appears, and it is where this is also one of the advantage of your C13 spectra. And the overlapping is minimized with signal overlapping, because the C13, it gives only the line spectrum. So the overlapping, there's no possibility for the overlapping of signals, and it is minimum here. and direct observation of non-protic functional groups which are not attached to hydrogen, such as cyanide and carbon, right? So carbonyl, CO, ketone, and acetylene. Okay, so you can direct observe of these particular non-protic functional groups here, and it is possible to identify the carbon backbone structure. So these are the advantages of your PMR here, proton NMR spectra, and also you can detect the mixture uh, in a sample, right? So you can detect the mixture in a sample, and it is very easy to detect that one. And recording of C13 spectra, generally we have various methods to record the C13 spectra. One is the CW method, that is a continuous wave method, and frequency sweep method here. And types of C13 spectra. So we have variety of C13 spectra like undecoupled spectra, broadband decoupled spectra. We call it as BBB. Okay, BBB spectra, and off resonance decoupled spectra, and selective decoupled spectra. So these are the various types of C13 spectra here, and undecoupled spectra. So undecoupled spectra, where generally here, where the carbon-carbon coupling is observed, and here you see the coupling of the carbon with the neighborhood carbon here, right? So this carbon-carbon coupling is giving the signals, multiplate signals here, and broadband spectrum. So generally, the broadband in the broadband spectrum, where the carbon is coupled with the protons here, and we'll get the signals according to the protons attached to the directly attached to the carbon here. Okay, so for example here you see get the CS3 CS3. Okay, so for both the carbons, okay, but these two methyls are falls in the same chemical environment, so we'll get only one signal for this one. And you see you will get the quartet for this one because the carbon is attached with three protons. Okay, and as per the n plus 1 rule, so we get the quartet for this CS3 proton here. Okay, and here you can see the in the ether. Okay, so this is the methyl ethyl ether, so where it is having the three non-equivalent protons here, yes, sir, carbons. There are three non-equivalent carbons. Therefore, you get the three signals with a different multiplicity. Okay, so for this methane, right? So methyl, which is directly attached to the oxygen, it appears as a four lines here, and the adjacent one on left side where the CS2 protons, it is appears as a triplet, and which is adjusted to the CS2, that is the CS3. Here is it is appears as a quartet here. And here is some ester compound is benzyl ester compound is there. So where it is having the five signals. Okay, so for the two two CS3, two ethyls, we have the two signals, and for this particular benzyl aromatic ring, we have the three. Okay, because we have the ortho para meta carbons here. So we get the three for the aromatic ring and two for the side chain here. And off resonance decoupled spectra. So generally off resonance decoupled spectra, we will double irradiation of the uh, group here, right? So double irradiation of the group. So where to reduce the noise of the signal, so we'll apply this particular off resonance decoupled spectra. And here is the calculation of the means the chemical shift values for this protons, carbons here. Here we see the for CH3, we get the quartet because we consider the protons directly attached to the carbon. isn't it? So for the CH2, we get the triplet here. For CH, we get the doublets. It is somewhat different than your H1NMR spectra. Here is some ethyl estate compound is given, and if you see the signals for this ethyl estate, where the CH3, okay, so the CH3 acetyl group here, acetyl group, acetyl CH3, where it is appears as a quadrate here because there are three protons directly attached to the carbon, so we get the quadrate for this. And this particular ester carbonyl group where it is having one right, so it is having carbon, so it is appears as a singlet because there is no protons attached to that particular carbonyl carbon here. Then this CH2 uh, it is having appears as a triplet because the carbon directly attached with the two, okay, so two hydrogens here. And this CH3 it is appears as a quadrate again because there are three protons directly attached to this particular carbon. And in the same in this particular ethyl benzoate also we will see the signals here, multiplicity. Like here for this ortho para meta, we'll have the different signals here. And where the ortho, it is appears as the doublet, and para also appears as a doublet here. And meta, ortho para meta. So these three carbons appears as the doublets. And where this particular ester carbonyl, it is appears as a singlet here. And this particular CH2, okay, it is appears as a triplet, and CSC appears as a quartet here. And aromatic ring CH appears as a doublet because the aromatic benzene CH, it is the benzene carbons attached with the one proton here. Yes. And para-ethoxy benzaldehyde. So if you see the off resonance decoupled C30 spectra, para-ethoxy benzaldehyde. So where this particular aldehyde group, aldehyde carbon is appears as a doublet because it is attached with the one hydrogen here. And then the ipso carbon, right, the ipso carbon, it is appears as the singlet because there is no proton directly attached to that carbon here. And with the ortho carbon, it is appears as a doublet, same as the meta also, it appears as a doublet because it is attached with one protons. Then the again the para carbon is appears as a singlet here. And in the ether, okay, in the ether linkages, where the CS2 appears as a triplet because that CS2 carbon attached with the two protons, and 2 plus 1 is 3 triplet. Then CS3 appears as a quadrat here. Next, selective decoupled proton decoupled spectra here. Okay, so when the generally the selective decoupled spectra, it is applied when the spectra is very complex here, right? So for the better resolutions, generally we'll go with this selective proton decoupled spectra here. So in this particular method, so what you do, simply will right, so we'll double irradiate the a particular group of carbon here. Then the instrument won't recognize that particular group, so it where the that particular the adjustment, it is becoming the uh, broad here, that signal is becoming the blur. Okay, so it is easy to, then the reasonable space is uh, right? The reasonable space is appears between the two signals. So clear separation. For the clear separation, better separation, we'll go with this one. Next, the chemical shift values of C30 spectra. And here is the generally we'll use the solvents to record the C13 spectra as your H1NMR spectra. So here also we'll use the solvents, and we will use the TMS as a reference one here, right? So reference TMS is the tetramethyl silane here. And why we are using the TMS means generally the TMS is the tetramethyl silane. So it is chemically inert. TMS is a chemically inert and it is carrying the four methyl groups, and it is appears at zero chemical shift value. So it won't interfere in the uh, spectra. And some other and the solvents usually used in this particular C13 spectra is CDCl3, with the signal multiplicity is appears as a triplet, and it is appears at 49 delta ppm here, and CS2Cl2 dichloro, okay, dichloro deuterated carbon here. So it appears as a quintet, and appears at 53.1 delta ppm, and here is a deuterated methanol. It is the split multiplicity is septate and appears at 29.8 delta values here. And various functional groups, they are showing the different delta values. We can see here is here is a ketones. Okay, the ketones they appears in the range of 205 to 220 delta values here, and with the carbonyl group in the aldehyde. In the ketone, it is 205 to 220, and the carbon, okay, the carbon which is a part of the aldehyde group, it is appears in the range of 190 to 200 here, and the carbonyl in the carboxylic acids and esters also. Okay, the carbon which is present as the CO, and in the acid and esters here, it is appears at 170 to 185, and carbon in the aromatic ring. Okay, so in the benzene and benzene related aromatic rings here, derivatives, benzene derivatives, it is uh, showing the delta values in the range of 125 to 150 here. And in the alkenes, the C double bond C, where the carbon is showing the delta values of chemical shift values of 115 to 140. And in the alcohol, right, in the alcohol carbon, it is having the delta value in the ranging of 50 to 65, and where this particular carbon, when it is attached with electronegative chlorine, it is having the delta value of 40 to 45 here. And the amine functional group, when the carbon is directly attached with the amine functional group, so we have the value in between 37 to 45 here. And in the tertiary carbon, okay, tertiary carbon, it is showing the delta value of 25 to 35. And this particular acetyl group carbon here, it is showing the 20 to 30. Okay, and with the secondary carbon, the tertiary carbon is appears in the range of okay, the tertiary carbon is appears in the range of 25 to 35, and the secondary is appears in the range of 16 to 25 here. And primary carbon, it is showing the delta value of 10 to 15 here. So primary carbon appears at 10 to 15, secondary 16 to 25, and tertiary in the 25 to 35 here. Right? These are the three different carbons delta values, and you can see the chemical shift values scenario in this particular graph. Next, the chemical shift equivalency. Right, so equivalent protons, sorry, equivalent carbons, non-equivalent carbons. Generally here in this particular ethane, CH3, CH3. Okay, so in the ethane, we have right? So ethane, we have two non-equivalent, sorry, only one equivalent set of the carbons here, because CS3, CSA both are same. So we'll get one set of carbons here, one type of carbons. And here is a tertiary butanol. Here two types of carbons, because all three CSDs are same, and where the central carbon is different here. So we get the two signals for this compound. And in this particular dimethyl benzene, where it is showing the three types of carbons here. And the chemical shift calculation. So chemical shift calculation here, the chemical shift of alkanes. So we can calculate manually. You can calculate the chemical shift values by using the some formulas here. So we have some increment values and standard values here for this alkanes here. Okay, so methane, where the it is a parent alkane, it absorbs it to minus 2.5 ppm here, and normal range of alkane is 0 to 60 ppm. Okay, so here the values, it is ranging from 2.5 to 45, and we have the additional values here. And to calculate the delta values, we have the formula. This is the delta equal to minus 2.5 plus the summation of Na. Okay, so minus 2.5 is the chemical shift values for this methane here, and A is the additive shift parameter, and the N equal to the number of carbon atoms for each shift parameter. Now we'll see the increment values for this additional values. Alpha, if the alpha carbon is there, so you have to add the plus 9.1. For beta, you add the 9.4 here. For gamma, you add minus 2.4. For delta, its value is plus 0.3 here. So like this, we can go with this chart here. Okay, so when the tertiary carbon, right? So when the here the quaternary carbon is having the primary carbon, then the value is minus 1. Okay, so when the tertiary carbon is carrying the primary carbon here, means where the quaternary, that particular quaternary carbon, around that carbon, the central carbon, if the adjacent, okay, the surrounding CS3 is there, that is considered as the primary here, then its value is minus 1.1. So likewise, we will go with this directions here. So we'll see one example for this calculation of chemical shift values for 3-methyl pentane. Okay, so for 3-methyl pentane, you see where it is having how many non-equivalent protons, non-equivalent set of protons are there. So there are 6 set of protons are there, isn't it? So now we can go with the calculation of this delta values for this 3-methyl pentane. Okay, like you see, first we'll take the value, means we'll substitute the value for each and every primary carbon, secondary, and all these things by taking the standard value minus 2.5. Yes, so here the delta C1 equal to minus 2.5 plus 1 into 9.1. Why we are taking the 9.1 here? So you go to the table. Okay, so where the 9.1 is for alpha carbon here. Okay, then plus 1 into 9.4. So it is beta carbon. So we have this alpha and beta carbons here, right? And some other values we are adding. And the calculated values, we got that 11.3. Okay, so by summation together, so we get the 11.3. That is a calculated value manually. And when we record the same compound, experimentally. So we'll get the observed value is 11.5. So very slight difference, very small difference is there. So it is acceptable calculation method here. And some other examples are given. So yes. Next, alkanes, when they are carrying the functional group here. So what are the additional values? We have this one. Like if here is the carboxylic acids are there in the alpha terminal, it is 21, and the where the internal value is 16, and beta terminal it is 3 here. Internal is 2, and gamma is -2. Okay, so like that, we can go with this calculation of this one. And for each and every means type of groups and compounds, we have the calculation methodology here. Yes. So next, the factors affecting the chemical shift values of carbon, the electronegativity. So generally here, presence of electronegativity, where the electronegativity is going to increases here, right? So presence of electronegativity atom, the value delta values are going to increase here. Okay, so when in any carbon is directly attached with the electronegative atom, the value is going to increase here. Here we will see with the CS3 in the alkane, okay, ethane, if you observe the delta value is 5.7, when the same ethane, okay, so it is attached with the in between the two methyls, if the oxygen is inserted, so then it becomes ether here. So where the value is going to 59.7. So what is happening here? The value is a tremendous increase of the value is taking place here, and the increase in the value is due to the that particular carbon group is directly attached with the methyl, and below also we can see that particular uh, ethylamine. Okay, ethylamine where this okay, CH3, CH2, NH2, where the CH2 group is directly attached with the NH2 here. Okay, so when it is directly attached with the NH2, so where the nitrogen is a more electronegative atom, so obviously its value is going to increase. That is at 35.9, and where the adjacent one, the CS3, where it is far away to this NH2, so its value is going to it is less, like 17.7 here. Okay, and here also we see in the ethyl chloride, where the CS3 moiety group is, it is far away to this, it is not directly attached with the chlorine here. So its value is 18.7, and CS2 its value is 39.9, because that CS2 carbon is directly attached with the chlorine here. So the electronegativity is going to increase the delta values. And anisotropic effect. So where the newly produced effect is unequal distributed in the molecule, so it is called the anisotropic effect here. Okay, so the due to the anisotropic effect, the carbons are having the showing the different delta values. Okay, the mesomeric effect. So generally here the mesomeric effect means the delocalization of effect here. So here the presence of electron withdrawing group it is causing the desilting effect here. So in this example, we can see here is CH3, CH double one CHO CH3, where the oxygen, the lone pair electron on this oxygen, it is okay. The lone pair electron is it is polarizing towards. It is involving in the resonance delocalization here. It is polarizing towards the CH. Then this pi bond is polarizing on the CH here. So we are getting the resonance structure of this one. So where it is causing for the increase of the electron density on that CH group. So therefore, where the electron the means the shift is upfield here, where the decrease in the delta values here. Yes, here the hydrogen bonding, and generally the hydrogen bonding. Okay, so hydrogen bonding is plays very important role in the chemical shift values. So presence when the group is involving in the hydrogen bonding, so its delta value is increases higher. If it is free from the hydrogen bonding, so the value is less here. For example, here in the benzaldehyde, the benzaldehyde is not involving in the hydrogen bonding, so that carbon, the aldehyde carbon, delta value is 191.5 here. Okay, so its value is 191.5. And when this benzaldehyde is involving in the intramolecular hydrogen bonding, okay, so its value is 196.9 here, right? So where the aldehydic carbon is involving in the intramolecular hydrogen bonding, okay, and here also like acetophenone, okay. So in the acetophenone also we can see the same difference, means same scenario we'll observe with the this particular carbon, okay, acetyl carbon without hydrogen bonding, no hydrogen bonding. So its value is 195.7 here. And when this particular acetyl group carbon is involving in the intramolecular hydrogen bonding with OH group here, so its value it becomes 204.1, right? So the additional delta value, the increased delta value is due to the involvement in the hydrogen bonding here. And the isotopic effect. So generally here the replacement of hydrogen atom by deuterium atom, so it results in the upfield up to 1.5 ppm. Okay, so the exchange of the higher isotopes here, so it is causing for decrease in the delta values here, where you can see here CS3, CS2Cl2, dichloromethane, where the delta is 53.8. When the hydrogen is replaced with the deuterium, so its value is 53.1. So you can see the decrease in the value here. Okay, and CD chloroform, where the value is 78 here. Chloroform carbon delta value is 78, and when the carbon is exchanged with the deuterium, higher higher isotope of hydrogen here, so its value is 77. So you can see the falls in the decrease in the delta values here. And some other factors like pH and electronegativity are there. Next, the couplings in the C13 NMR spectrum. So generally we have two types of couplings here, homonuclear coupling and heteronuclear coupling. As a homonuclear coupling is in between the carbon-carbon, and a heteronuclear coupling is in between the carbon and hydrogen here. Okay, so here first we'll see the heteronuclear coupling. So here the coupling between the carbon C13 and hydrogen here. Here is coupling between C13 and other nuclei like fluorine and phosphorus, all these things here. So first we'll see the heteronuclear coupling, one bond coupling. So one bond coupling generally when the particular hydrogen or any fluorines are directly attached to the carbon, so it is one bond coupling here. So J we indicate with the J1. One means only one bond here. Okay. Next, two bond coupling. So generally, the two bond coupling means the adjacent one, the coupling with adjacent 1,3. Okay. So here you see. Yes. Right. So here that the coupling between carbon and hydrogen separated by two bonds is known as the J2CS coupling here. That means a separation. Okay. So separation, the two bond separation here. That is a Wiener coupling. Simply, we called it is a Wiener coupling here. On same carbon, so we called it is a geminal coupling and three bond coupling. So where the separation of the okay coupling atoms with two more bond in between the coupling groups. There are two atoms are there. Okay. Next application of C13 spectra. And generally the C13 spectra, it is applied in variety of fields here. Generally, first we'll apply this spectra, C13 spectra for the structural identification. Okay, so it is very useful spectra to distinguish the isomeric paraffins here. Okay, so here we'll see the mix the isomers. Okay, that positional isomers and the chain isomers will be identified with this C13 spectra. Here, the one example is given, like you see, it is yeah, it is an hexane is given, right? So an hexane is given, and here is a iso isopentyl. An hexane and isopentyl. We have the okay. So in the H1 NMR spectra, okay, in the H1 NMR spectra, generally how many signals you will get for this N hexane? So generally we'll get the one, two, three signals you will get for this one. Okay. And for this isopentyl, isopentane, so how many signals you will get for this? Here is one, two, three, and four, five. Okay, so there are five signals you will get for this. Okay, so one, two, three, four, five. Five signals are obtained. And for this particular N hexane, we get the three. And for isopentane, we'll get the six signals, sorry, five signals for this one. Right? So generally here in the C13 spectra, okay, in the C13 spectra, with the difference in the chemical shift values, we can identify the two isomers here. Okay, the two chain isomers. Here is C1 and C4 in the N hexane. You can see C1 and C4. So it shows the delta value of 14.1, and C2 and C5 it is showing the 2.3, and C2 and C6. So we get the 32.2 delta values here. And isopentane it gives the four signals, isn't it? So isopentane, so it gives the four signals where the C1 and C5, where it is having the 22.2 delta values, and C2 it is showing it 31.1 delta value, and C3 it is showing the delta value 32. and C4, you will get the delta value of 11.7 here. Okay, so you can calculate the delta values by using the manual calculation formula here. Okay, the alkanes chemical shift value calculation minus 2.4 plus that is epsilon Na. Okay, so here the by this deltas chemical shift values and the number of signals, you can differentiate these two isomers, the chain isomers here. Okay, and some other applications are there. So we'll see in the next class.